Sometimes when drawing Lewis structures, you can draw more than one appropriate Lewis structure to represent the molecule. In this case, we use resonance structures to show the average Lewis structure when more than one valid structure can be drawn. The real structure is an actual hybrid between all of the resonance structures that we can show for a single molecule. Draw resonance structures for the nitrate ion NO3-. Our valence electrons for NO3- are going to be 5 for nitrogen, 6 for oxygen, times 3 because we have 3 oxygens, plus 1 for the negative charge on the ion to give us a total of 24 electrons. We previously drew this molecule and came up with this as our Lewis structure, where we had 3 lone pairs on 2 of the oxygens and 2 lone pairs on one of the oxygens that was double bonded to the nitrogen. We also included brackets and charge around the molecule because it was an ion, and we wanted to show that charge. When we have resonance structures, that means we have multiple bonds that are able to be moved to other locations. For example, our double bond could be on the top oxygen, or it could be on one of the other oxygens. We could also show the double bond right here. If we did, we would have to put a single bond for the other oxygens. So placing our 24 electrons, this could also be an appropriate structure that we draw for nitrate. When we have resonance structures, we use an arrow with 2 heads on each end to represent resonance. So this is called a resonance arrow. And for NO3-, we have one more resonance structure that we could draw. We could show the double bond between nitrogen and oxygen on the oxygen in the lower left corner as well. Remembering to still include brackets and charge on the outside. This means that the bonds between nitrogen and oxygen in the nitrate anion are not single bonds, nor are they double bonds. They are somewhere in between a single and a double bond. All 3 bonds are identical. Since all bonds are the same, this is why we use resonance structures to represent the different locations that the electrons could be. Draw resonance structures for the nitrite ion, NO2-. If we take up a tally of our total valence electrons, there'll be 5 for nitrogen, plus 6 for each oxygen, times 2, because we have 2 oxygens, plus 1 for the negative charge on the ion. Our total electrons we have to place would be 18, and our Lewis structure that we drew for the nitrate ion was nitrogen with a double bond to one oxygen and a single bond to the other oxygen. We had 2 lone pairs on the double bonded oxygen, 3 lone pairs to complete the octet on the outer oxygen, and we ended up with a lone pair of electrons on the nitrogen. We included our brackets and our charge around it. And in this one, we would only have one other resonance structure to draw because we could have swapped the locations of the double bond and the single bond. So we could put a single bond oxygen on the left-hand side and a double bond oxygen on the right-hand side. We still would have complete octets on all of our atoms, and there would still be a lone pair on the central atom. But we showed that the double bond could be either on the left or the right-hand side by drawing the resonance structure. So the bonding between nitrogen and oxygen isn't a double bond and it isn't a single bond. It's kind of like a 1.5 bond because the resonance structures are trying to represent that there's multiple Lewis structures that this molecule could have that are completely accurate. Bond order is a measure of the amount of electron density in a bond. The bond order can be calculated by using the following formula. The number of bonds around the central atom divided by the number of atoms that are around the central atom. For many simple molecules, we can look at the Lewis structure to determine the bond order. A single bond has a bond order of 1. An example of this could be fluorine or F2. If we look at the Lewis structure for F2, we can see that we only have one single bond present in its structure. Therefore, its bond order is 1. A double bond would have a bond order of O2. If we look at the Lewis structure for oxygen, which is O2, we can see that we have 4 electrons in the middle, which is 1 double bond. So therefore, we would say the bond order is 2. And a triple bond, we could use an example of nitrogen, which has 1 triple bond between each nitrogen atom, and therefore the bond order is 3. Some Lewis structures that we draw actually have fractional or decimal bond orders that fall somewhere in between 2 bond lengths. Calculate the bond order in the nitrate ion NO3- and the nitrite ion NO2-. How do they compare in bond length and bond energy? So let's start with NO3- on the left-hand side. Bond order is calculated by taking the number of bonds around the central atom divided by the number of atoms around the central atom. So if we assign each one of our bonds a number, our single bond we can give a number 1. So we have 1 single bond here, another single bond there, each will get 1. Our double bond would be assigned 2. So in our numerator for our bond order calculation, we're going to have 1 plus 1 plus 2. That's our total tally of the number of bonds. And how many atoms are those bonds spread out over? So we have 1 atom, 2 atoms, 3 atoms, because we have 3 oxygens that those bonds are spread out amongst. So we would divide by 3. Therefore, our bond order for NO3- is going to be 4/3, which is about 1.3 repeating. Now let's calculate the bond order in the nitrate ion and make some comparisons about the two. Our bond order can be calculated by determining how many bonds are around the central atom. In this case, we have 1 single bond that gets a bond order of 1, plus we have 1 double bond, which will get a bond order of 2. So 1 plus 2 divided by how many atoms are around the central atom. We have 1 oxygen and we have 2 oxygens. So in this case, we're going to divide by 2. So our bond order in the nitrate ion is 3/2, which is equal to 1.5. Both of our bond orders for nitrate and nitrate fall somewhere in between a double bond and a single bond. If you recall our trend, single bonds versus double bonds, a single bond is going to have lower bond energy, but a longer length between the bonds. Whereas our double bond is going to be higher in energy, and it's going to be shorter in length. A pure single bond would have a bond order of 1. A pure double bond would have a bond order of 2. We just calculated our bond orders for NO3- and NO2-, and we can see where they fall on this scale. We would have 1, and then 1.3, and then 1.5, and then up to 2. Therefore, a molecule that has a bond order of 1.3 is going to have the lower bond energy and the longer bond length. Whereas a molecule that has a bond order of 1.5 is closer to 2, so it's closer to a double bond. Therefore, it's going to be higher in bond energy and shorter in length. We can only come up with this analysis by making comparisons between the two numbers that we calculated. Calculate the bond order in the sulfate ion, SO4 and the sulfite ion, SO3 How do they compare in bond length and bond energy? Starting on the left-hand side, we have our bond order calculation, which will be first determining the number of bonds. So we have 1 single bond that'll get a bond order of 1, another single bond which will get a bond order of 1, and a double bond which gets a bond order of 2. So this is going to be 1 plus 2 on the numerator, and those bonds are spread out amongst how many atoms? We have 1 oxygen, 2 oxygens, and 3 oxygens. So we have to divide by 3. In this case, our bond order will be 4/3, which is equivalent to 1.3, repeating. In our SO4 ion, if we calculate our bond order, we're going to have 2 double bonds. They each will get a bond order of 2, and 2 single bonds, which each will get a bond order of 1. So we would have 2 plus 2 plus 1 on our numerator, and then dividing by our number of atoms, we have 1, 2, 3, 4 oxygen atoms that those bonds are spread out over. So we're going to divide by 4. In this case, we're going to come up with 6 over 4 for our fraction, which is equal to 1.5. So now we can make comparisons between sulfite and sulfate to determine who has the longer bond length, who has the shorter bond length, who has the higher bond energy, and who has the lower bond energy. 1.3 is less than 1.5, so the bond order of 1.3 is going to be closer to a single bond, whereas the bond order of 1.5 is going to be closer to a double bond. Therefore, our 1.3 bond order will be lower in energy and longer in length. Our 1.5 bond order will be higher in energy and it will have a shorter bond length. So the SO length, the SO bond length in SO42- is shorter than the SO bond length in SO3-, because that bond order is higher for sulfate than it is for sulfite. When we are following the rules for drawing Lewis structures, sometimes it's possible to come up with multiple structures that follow the rules and are technically correct, but we often want to determine what the best Lewis structure is. A concept called formal charge allows us to determine what the best Lewis structure is when you can draw multiple structures. Formal charge is an electron bookkeeping method that indicates atoms that have extra or less electrons around them than they would technically prefer to have. A formal charge of 0 is preferred, or essentially having no formal charge. The best structures place negative formal charges on more electronegative atoms. So recall our trend for electronegativity across the periodic table. Electronegativity increases from bottom to top within a family and from left to right across a period. Also, the sum of the formal charges must always equal the charge on the species. If we have a neutral species, the formal charges will add to 0. If we have a species that has a -1 charge, the formal charges would add up to -1. To calculate the formal charge on an atom and a molecule, we take the number of valence electrons that that atom should have from the periodic table, and recall we figure out the number of valence electrons by looking at the group number. And we subtract off its associated electrons. The associated electrons come from the structure that we drew. Electrons that are considered associated are half of the bonding electrons and all of the non-bonding electrons. This will be best explained by doing an example. Assign formal charges to each atom in the following structures for CO2, and then determine the best Lewis structure. So how I like to determine formal charges is I like to break all of the bonds in half by drawing an imaginary line separating the bonds between the central atom and the outer atoms. And then I use the formula for calculating formal charge. So let's start with the oxygen on the right-hand side. Oxygen on the periodic table is in group 6A. That means that oxygen likes to have 6 electrons around it. We're going to subtract off how many associated electrons it has. Associated electrons are all of the non-bonding, so notice it has 2 non-bonding electrons right here and 2 non-bonding electrons right here, so there's 4 non-bonding electrons, and then half of the bonding electrons. So if we were to cut those bonds in half, 1 electron would go to the carbon, 1 electron would be associated with the oxygen. And since it's a double bond, we have another 1 electron associated with carbon and another 1 electron associated with oxygen. So there's 2 more associated electrons because half of the bonding. So we have 6 minus 6 electrons, so our formal charge is 0. That's the preferred formal charge because anytime we have formal charge, an atom will either have less electrons or more electrons than it wants to have around it. Let's go to the outer oxygen. In this outer oxygen, we're going to start the same. It's in group 6A on the periodic table. So that's our number of valence electrons, and we're going to subtract off its associated electrons. So all of its non-bonding, so 2 non-bonding, 4 non-bonding, and then half of its bonding. So 1 electron to the oxygen, 1 electron to the carbon, In the double bond, we have one more electron to the oxygen and another electron that's associated with carbon. So we have two more electrons from the bonding. So we're going to have 6 minus 6, which will equal 0. And that oxygen was identical to the oxygen on the right. So both of them have a formal charge of 0. And for carbon, carbon is in group 4A on the periodic table. So it wants to have 4 valence electrons around it, minus its associated electrons. If we count our associated electrons, we're only going to be counting the bonding electrons because there's no non-bonding electrons on carbon. So we've got 1, 2, 3, 4 associated electrons. So we're going to have 4 minus 4. Therefore, carbon has a formal charge of 0 in this structure. Both oxygens and carbon having a formal charge of 0 makes this a very good Lewis structure. Let's calculate the formal charges on the atoms in the structure below it. This is another appropriate Lewis structure that we saw we could draw for CO2. Everyone has a complete octet, so it is technically appropriate. Draw your line to break the bonds between the atoms. Let's start with the outer oxygen on the right-hand side. We know oxygen's in group 6A, so it wants to have 6 electrons around it. And we're going to subtract off its associated electrons. So all of the non-bonding, we have 2, 4, 6 non-bonding electrons, and then half of the bonding electrons. So all we have is a single bond here, and a single bond is 2 electrons. One is associated with carbon, and one is associated with oxygen. So our total electrons around oxygen are 7 in this structure. So we're going to have 6 minus 7, or the formal charge on oxygen would be -1. Let's do the oxygen on the left-hand side now. We're going to have our group number, which is our number of valence electrons, 6 for oxygen, minus, we have 2 lone electrons, and we have 1, 2, 3 from half of our bonding. So we're going to have 5 associated electrons total, so 6 minus 5. The formal charge on the left oxygen is going to be +1. So +1 on the left-hand oxygen, -1 on the right-hand oxygen. And for carbon, we're going to have 4 valence electrons from the group number, so group 4A, minus how many associated electrons does carbon have? It has no non-bonding, but it has 1, 2, 3. That's half of its bonding, plus 1 more over here. So we have a total of 4 associated electrons. So 4 minus 4 will give us a formal charge of 0 for carbon. So in both structures, carbon had a formal charge of 0, but on the bottom structure, we had formal charges of +1 and -1 on both of our oxygens. Therefore, just by the fact of having formal charge, that makes that a worse structure than the top one. So our top structure, we would say, is our best Lewis structure, because it minimized the amount of formal charge on all the atoms. Given the two structures of ClO3-, assign formal charges to each atom and determine the best overall Lewis structure. So let's start with the Lewis structure on the left for ClO3-. We're going to draw our imaginary line that's going to break each of our single bonds in half. And we know when we break that single bond in half that 1 electron is going to go to each atom. So we're going to have 1 electron to the oxygen and 1 electron to the chlorine. And then we're going to use our formula in order to calculate formal charge for each of these atoms. So for oxygen, oxygen is in group 6A. That means it likes to have 6 valence electrons around it. And we're going to subtract off how many electrons it actually has. When we look at our non-bonding electrons, we have 2, 4, 6 non-bonding electrons, plus we have 1 associated electron from half of the single bond. So we have a total of 7 associated electrons around our oxygen. So that means we're going to have 6 minus 7, which means our oxygen has a formal charge of -1. And all 3 of our oxygens are identical. So we're going to have 6 minus 7, or a -1 for this oxygen. And we're going to have 6 minus 7, which would be a -1 formal charge for this oxygen, just because they're all identical. For our central atom, we have chlorine, and chlorine is in group 7A. It's a halogen, so it wants to have 7 electrons around it. And how many electrons does it have? It has 1 non-bonding pair, so 2 associated electrons from the non-bonding, and then half of the bonding. So we have 2, 3, 4, 5 total. So we're going to have 7 minus 5, which would give us a formal charge of +2 on our chlorine. So in this Lewis structure, every single atom has a formal charge on it. None of them had a formal charge of 0. It's probably not going to be our best structure that we could draw. Let's check the structure on the right. Chlorine in this structure has 2, 4, 6, 8, 10, 12 electrons around it, but that's okay because chlorine is in the 3rd period or lower, therefore it can have expanded octets. So what happened is 2 of the lone pairs on this oxygen and this oxygen were moved over to create 2 double bonds. And let's break our bonds in half and assign an electron to each side. So 1 electron goes to oxygen, 1 to chlorine, 1 to oxygen, 1 to chlorine, 1 to chlorine, 1 to chlorine, 1 to oxygen, 1 to oxygen, and then our single bond, 1 to chlorine and 1 to oxygen. Start by calculating our formal charge for the oxygen on the right-hand side. We're going to have 6 electrons from the periodic table. That's how many valence electrons it has. Minus, we have 2, 4, 6, and then half of the bonding, 7 associated electrons. So 6 minus 7, we're going to have a formal charge of -1 on that oxygen. Let's do our oxygen on the top. So we're going to have 6 valence electrons minus, we have 2, 4 from our non-bonding pairs, and then we have 2 more from our associated electrons here. So in this structure, our oxygen is going to have 6 total associated electrons. So 6 minus 6 is 0. That means our oxygen has no formal charge. And it's actually going to be the exact same for this oxygen here. We're going to have 6 minus, we have 2 lone pairs, so 2, 4, and then half of our bonding, 6 here. So 6 minus 6, or 0 formal charge on the other double bonded oxygen. And lastly, we have to calculate any formal charge on our chlorine. Our central atom is a halogen, so it likes to have 7 electrons around it. Minus, how many does it have? It has 1 non-bonding pair, so 2 electrons from that. And we have 4, 6, 7. So here we're going to have 7 minus 7, or 0 formal charge. So in the structure on the right, the only species that had formal charge was this oxygen right here, which had a -1 formal charge. Everyone else had 0 formal charge, which is preferred. And if you have to have formal charge, it's better to have a plus formal charge on an electropositive atom or a negative formal charge on a more electronegative atom. Oxygen is fairly electronegative. It's pretty high in the upper right-hand corner on the periodic table, so it can bear a slight formal charge. But that means that this is going to be our best Lewis structure between the two of them, because the structure on the right, we had a +2 formal charge on chlorine, which is definitely not preferred since that's a really electronegative halogen. And we had formal charges on all of our oxygen atoms. We can use Lewis symbols in order to diagram the electron transfer that takes place in ionic bonding. We do not draw Lewis structures in order to represent ionic bonds because Lewis structures are only used for molecules, which are 2 or more nonmetals together. When we're trying to represent ionic bonding, we can go back to using Lewis symbols, which is the symbol for the element surrounded by the number of dots that are electrons that represent their number of valence electrons. For example, if we want to show the ionic bonding and the formation of sodium chloride. Sodium is a group 1A metal, and since it's in group 1A, it has 1 valence electron. Chlorine is a group 7A nonmetal. Since it's in group 7A, it has 7 valence electrons around it. In order to have a complete octet, sodium can give up 1 electron, and chlorine can accept 1 electron. That way they both can have a complete octet of electrons from this process. So sodium will give up 1 of its valence electrons to chlorine, which will accept it. When sodium gives up that 1 valence electron, we have sodium that's left with a +1 charge. And when chlorine accepts another electron, we have chlorine that now has 8 electrons around it, which we call the chloride anion. So it has a negative charge now because it has an extra electron. This represents the ionic bond that we see in sodium chloride between a metal cation and a non-metal anion. Ionic bonds are really just the attractive forces that are holding together positive and negative charges. Let's try to use Lewis symbols to show the bonding in something like magnesium oxide next. So magnesium oxide is MgO. Magnesium is a group 2A nonmetal, therefore it has 2 valence electrons. Oxygen is a group 6A nonmetal, therefore it has 6 valence electrons around its Lewis dot symbol. When we form magnesium oxide, magnesium has to lose 2 electrons in order to have a complete octet, whereas oxygen wants to accept 2 electrons. So both of our electrons on magnesium will be given up to oxygen. When we form our products, we're going to have the magnesium ion, which will have a +2 charge, and we're going to form the oxide anion, which will have 8 electrons around it, and since it gained an extra 2 electrons, the oxide anion has a -2 charge. So magnesium oxide is held together by a bunch of +2 and -2 interactions that we use to represent the ionic bond. Remember, ionic bonding is electron transfer. Whereas with our Lewis structures for molecules, they were sharing electrons. That was why we could draw a Lewis structure in the first place. So whenever we're showing ionic bonding, we want to use Lewis dot symbols. Use Lewis symbols to diagram the formation of the ionic bond in lithium sulfide. First, let's write the correct formula for lithium sulfide. Lithium, we know, is a group 1A metal, so it forms a +1 charge. Sulfur is a group 6A nonmetal, so it forms a -2 charge. When we come up with the correct formula, we want to cross the charges, and so we're going to have Li2S. That tells us that there's going to be 2 lithium ions for every 1 sulfide anion. Let's draw our Lewis dot symbol for our 2 lithium ions. Lithium's group 1A, so it has 1 valence electron, and we're going to have 2 of them in this reaction. Sulfur is a group 6A nonmetal, and it has 6 valence electrons around it. So 1, 2, 3, 4, 5, 6. In this example, lithium is going to give up 1 of its valence electrons to sulfur, and another lithium atom is going to give up another valence electron to sulfur. So we're going to have this 1 electron form a pair here, and this other electron form a pair here. That is how sulfur will have a complete octet. It'll gain 2 electrons from 2 separate lithium ions. And so we end up forming 2 lithium +1 ions, and we have 1 sulfide anion that has a complete octet, and each sulfide ion has a -2 charge. So when we add up the total of our charges, they add to 0 because we have 2 +1s and 1 -2, which is what we would have saw when we did the nomenclature chapter. Use Lewis symbols to diagram the formation of the ionic bond in calcium bromide. Our formula for calcium bromide, calcium is a +2 charge, bromine is a -1 charge. So our formula for our neutral compound will be CaBr2. That means that for every 1 calcium ion, we're going to have 2 bromide anions. Calcium, we said, is a group 2A metal, so it has 2 valence electrons around it. Bromine is a group 7A non-metal, so it's going to have 7 valence electrons around each of them. When we form calcium bromide, we're going to see electrons transferred from the metal to the nonmetal, so they each can have a complete octet. Calcium will give up one of its valence electrons to one bromide atom to become the bromide anion. It'll give up another one of its valence electrons to the other bromine atom. So what we're going to get for our products is we're going to have one calcium 2+ ion that forms from the result of the loss of its 2 electrons from the valence shell. And we're going to form 2 bromide anions. Each one will have a -1 charge. This represents our ionic bond between calcium and bromine.